Okay, good afternoon. I think around 20 people are there. Hope they will join slowly. So 15 along with me. We were in the fifth unit. So some important unit, this unit. Last class in the regular class, I was talking about the fifth unit. Here important thing is to calculate the residence time distribution, RTD. And then there are some curves. The relationship between the curves. That is what. Next, models. So today we will cover this, how this and this, right? So PFR is no actual mixing, MFR is complete mixing should be there, but in general, here there won't be some people muted. Here no actual mixing, but actual mixing. Complete mixing should be there in CSTR, but there may not be complete mixing here. How much it is deviating from the ideal? That is what we will measure by this RTD method. These are some of the deviations, stagnations, bypass, channeling, recycling, some vertices which are being formed. This all I think we discussed in the earlier class. Here important three factors which you need to consider when you are designing the reactor, real-time reactor is, one is the RTD, the other one is state of aggregation and the mixing, right? So we'll first see what is this RTD, how to calculate and what are the curves available for them. Then we go for these two later, right? So whatever discussion I'm going to make is only for RTD now, right? So this all I think we discussed. Here one important thing is to calculate this E curve. E curve is nothing but exit age distribution. So exit age distribution is the molecule which is staying inside the reactor, how much time it is spent inside the reactor. So if you draw a curve versus time versus that particular concentration, then you get E curve, right? So to measure that, we are discussing yesterday last class that you have to send someone inside, right? That someone is nothing but a tracer, chemical tracer. So when you are giving a tracer, it should be that like a dye, right? Tracer is nothing but a dye which is easily detectable. It should be completely miscible. It should not react with the reacting systems. It should just follow the path of that. So physical properties should be same as that of this dye to that of the reacting system and should not absorb on the walls, right? So based on that, there are four inputs in the last class. We were discussing this. Pulse input, step input, periodic and random. So for each input, you give the exit, that is output curve will be different again. Output curve will be different. If you give a pulse input, you can see this is the pulse. Short T period, you are giving in whatever you want, just like a syringe. In syringe, you are if you take a dye and then inject inside, that is nothing but a pulse or impulse input. Pulse input in the sense if it is taking more time, it is pulse to send. If you are forcing very fastly, then it is impulse, like a direct delta function, right? Mathematics people call this impulse input as direct delta function, right? The area under the curve should be 1. I think you might have studied about all that. This is the step input. If you give a step input, the output also will be different. If you give a pulse input, output will be different. And if you give a periodic input, just it is periodic input is nothing but a series of pulse input. Here you give a pulse, again you give a gap, again you give a pulse, right? So series of pulse input is nothing but a periodic input, sine curve. And then your output, if you see the concentration here, if you put a sensor and measure the concentration, you get a one different curve. If you give a cyclic input, the output also will be cyclic, just like that. Random input, the output also will be random, right? Now you see, you are giving us low die, high die, too much of die, again too much of die. So it goes on increasing like this, whatever way you want, right? So these four, if you give each input, the output will be different. Output will not be same. If you give a pulse input, you get one type of a curve. If you give a step input, you get a different curve. If you give a pulse input, periodic input, you get a different curve. If you give a random input, you get a random curve. So here we won't go for this. We won't go for this. In our syllabus, we go only for pulse and step input. This periodic input, you can see in process control, will next semester it will come process control. In control, so lot of, if you want to control, you'll give lot of sinusoidal input. Periodic input is nothing but a sinusoidal. That time you can see that. Let us not waste the time here, right? So only two is very important: pulse and step. Pulse in the sense you are giving just opening the wall and closing. That's all. Just I gave one example. If you want to open the wall, so open the wall, close immediately. That is pulse. Otherwise, you can open the wall, keep for some time, and then close the wall. That is also pulse. So the time, how much you are giving in between. If you are immediately closing, then a pulse becomes impulse. Pulse input becomes impulse. And if you are giving some time, then we call it as a pulse input. Though we are calling it as pulse, it is impulse also. Physics. What is impulse? Impulse? I don't know whether you remember. Due to that only, all the glass vessels or whatever they want to transport, they put that bubble type packing and all. No? So to reduce that, right? So large force acting on a short particular time. That is the impulse, right? Then step input, right? So these two are very important. We'll see these two now. Now, what is pulse input? This pulse input, you are giving, this is the input pulse, and output you get a curve like this. This is the C pulse, and this is the time. This is the time, right? So what is this? Now you see, this is a plug flow reactor, which is having a volume of V. So you are having a what do you call wall. Let the flow rate be V meter cube per second, volumetric flow rate, and output also is a flow rate. You are putting a detector here to detect the concentration of this particular thing, right? So you are introducing a pulse. So what you introduce a pulse? Pulse is nothing but a tracer, which is input. So you are giving a pulse input. Pulse in the sense the input curve will be like this. What is this? We call in terms of direct delta function. Instantaneously introduce m units of tracer into the flowing fluid. Just like you take a syringe, some 5 ml you want to introduce, you put a syringe here and then inject all that. Pulse input is nothing but injecting through a what do you call syringe or whatever it is. Or if it is a wall, just open the wall, close the wall. So that this entire M units, whatever units you want to put, you are giving M units or whatever unit may be of thing. If you want to send some 5 grams of what do you call dye, you put 5 grams or whatever may be the unit. What if it is a liquid, some 5 ml or whatever it is, right? So this liquid is going, and now at time t is 0, you are not introducing any tracer. Time t greater than 0, you are introducing the tracer, some m units. Then what will happen? Now output, you put a sensor here and measure the concentration of the tracer. Measure the concentration of the tracer. Tracer is not reacting with this particular thing, but it is miscible with this. And tracer you can easily identify. That is what is the conditions for it. It should completely soluble. It should not be reactive. The properties of the tracer, you have to see to that your tracer, what you are putting, is having the same properties as the flowing fluid, right? So if you put a sensor here and try to measure the concentration of the tracer and plot it, then what will happen? This is the concentration of the tracer with respect to the time. Time t is equal to 0. There is no tracer which is coming here because you are putting here. If it is ideal, what will happen? This entire fluid, because you are introducing here, right? So the fluid which is having here, this is called as the Volder fluid, right? Volder fluid, which is there, or this should not mix this particular thing. Only this. Then what should come? Your ideal behavior, it should come like this. Am I right? Because till here, till this some time, there should not be any tracer because this is not getting mixed. Therefore, this fluid will move, this section moves, this section moves, this section moves, this section moves, this section moves. When this section is going out, this section will come to here. I'm titling like a pack of cards, right? So one card you remove, the other card it is coming. It's not that this card will come out. So should have some time here. Then it is ideal. But ideal, there are some non-idealities due to that this fluid suddenly it may come out. That is what is happening here. If you are cutting means at this particular time itself, you are having the concentration of the tracer. That means that there is something mixing here. That is why this tracer is coming out much before. Because if this is taking some T bar time or T, that is the mean residence time, but it is coming much lesser than T time. If you are assuming this is the T bar or mean residence time, your fluid is coming much before and fluid is coming afterwards also. It should not happen. If it is ideal, it should be like this. Am I right? So that is what we are trying to measure. So how much of the fluid is coming front? How much of the fluid is coming after? So if I draw a curve, a smooth curve, some points I will get with the different times. And if I plot this and a smooth curve I get, right? So if this curve is not meeting this, that means that some of the tracer is inside because you know how much of the tracer you are sending inside, maybe 5 ml or whatever it is. Right? That means that there is some dead spots here. Then only it should go like this. It won't touch this. Now once you are having the curve, you know that this is a direct delta function. The area under the curve should be giving you the volume of this fellow. That is how much you are putting. So evaluate the area under the curve. Area is nothing but integral 0 to infinite c dt. So C1 dt1 plus C2 dt2, C3 dt3, like that it goes on. So you have to calculate the area under the curve. So either you can use Simpson's rule or you go for this number of rectangles and then average it out. Simpson's 1/3 rule or 3/8 rule or whatever area under the curve you can calculate, right? So this is nothing but sigma Ci delta Ci, C1 delta C1, C2 delta DC2. So you are having some different terminology here. This is the delta T, these two, right? This is the delta T. Delta T into this particular thing will give you a total thing. Like that, that plus this section, that plus this section. So entire section will be equal to the area under the curve. Now you want to calculate what is the mean residence time, because when there is a bell-shaped curve, and if you are trying to, you have to see how much it is skewed, right? Statistics, all the mathematics statistics will come. Now you want to find T bar. Once you find T bar, then you can find your variance also, how far it is being moved from this side to that side, right? So to calculate T bar, integral T C delta T, that is integral Ti Ci delta Ti divided by integral C delta T is nothing but sigma Ci delta Ti. So Ci into delta Ci is nothing but this section into the time will give you time variance of that concentration divided by the concentration with the sum will be giving you T bar, because T bar is here You are multiplying, you are dividing it. So T bar will remain the same. Ci delta Ci get cancelled. So this is how the E curve will look like. Once you calculate the E curve, that is T bar, then you can calculate the variance also, right? Because T bar is here. So how much is moving this side? How much is moving this side? So T minus T bar whole square. You know that variance square, right? That we will see. Right? So we can calculate the variance. From the variance, we can know how much is the spread. How much is the spread along this T bar. So if your concentration, if your plug flow reactor is ideal, then your T bar should be equal to your T. That is the mean residence time. But since there is some non-idealities, your T bar and T will not be same. So how far it is deviating, that is what we will see by the variance. That is what how we have to do this E curve, right? We'll show you one problem so that you will understand what is happening here. Now you see, the data given set below represents a continuous response to a pulse input in a closed vessel, which is a chemical reactor. Calculate the mean residence time. So T he gave you, C pulse he gave you. So that means what? T he gave and C pulse he gave. Therefore, T he gave, C pulse you gave. So whatever you are giving, you try to put a graph, right? So that is what we will do here. Now you see. So this is the mean residence time formula. T bar is sigma Ti, sorry, Ti Ci delta Ci by T, this one. What is delta Ci here? Delta Ci is nothing but the interval of times. So 5 minutes or 5 minutes, right? So delta T is constant, 5 minutes. T bar is nothing but sigma Ti Ci by Ci, right? Delta Ci constant. Therefore, delta Ci here and here, it gets cancelled out because it is 5. So how to do now? T1, C1. What is T1, C1? 0 into 0, that is 0. Next, T2, T1, T2 is 5, T1, C1. Yeah, sir. Yeah, T. 5 into 3, that is what here you are putting. 5 into 3. 10 into 5, right? Here, 10 into 5. Then 15 into 5. Is it correct? Yeah, 10 into 5, 15. So multiplication of these two divided by sigma Ci is nothing but this particular thing. Sum of this, that is for sum. So you are getting T bar as 15. So the mean residence time is 15. Right? Mean residence time is 15 because this calculate. Now you need to calculate the area under the curve. Area under the curve is sigma Ci into dCi. So delta Ci. Delta Ci is 5. Therefore, you have to multiply Ci with delta Ci. So instead of that, you can calculate all Ci into multiply by delta Ci since it is constant. If this time variable is changing, then you have to multiply Ci with the delta Ci individually. So this what you are sending is 100 grams, 100 gram minute per liter you are sending. That is the area under the curve, right? Area under the curve. That's what. Now you have to calculate the E curve. That is what it is being done. Now you have to calculate the area under the curve. Either you can do like this or you can do Simpson's rule, right? So let us see the area under the curve. This is the area under the curve. E versus T. So you have to calculate E. What is E? E is this. So you have to calculate the area under the curve. Area under the curve is 0 to infinite C dt. So C dt, area under the curve 0 to infinite. What we do is we try to split this particular thing. Instead of going from 0 to infinite, we go from 0 to 25 and 25 to 35. One second. 25 to 35 because you are having 35 is the limit here, right? So 0 to 25 CDT and 25. Please mute yourself. Now we use the Simpson 1/3 rule. So 0 to 25 is 1/3 rule is nothing but delta is 5 delta T divided by 1/3. Then multiply that first thing plus 4 times the second one and to normal. That Simpson's rule you have to put. Then you got this area. Now this area is again you are putting Simpson's 3/3 3/8 rule. You have to get this formulas. This is this. So your entire area under the curve is sum of this. That is what 101. The same thing we got here almost. That is what. Either you can do analytically or you can go for numerical methods. That's up to you how you want to do. If you can do this here itself, then it is fine. No need for you to go for these rules. Now E curve, what is E curve? Area under the curve you got. E curve is C divided by integral 0 to infinite CD. That is C divided by the area under the curve. This will come in terms of minute inverse, right? This is for pulse. So T is 5 minutes. C pulse is 3 liters per 3 grams per liter. So E curve becomes 3 divided by 100. That is what is the area under the curve, 0.3 minutes. So you can calculate the different E curves. For 3, it is right. You are having for 3. Then you calculate 5 divided by 100, 5 divided by 100. Like that, that is what you get. 5 divided by 100 is 0.05, 0.05, like that. Huh? Now you draw the E curve versus time. So this two, then this is the E curve, right? So this is how you have to do this particular thing. That is what I'll just show you in the presentations also. Now you can see here. The analysis. Yeah, this is what E curve is, C divided by C particular thing. How you are getting this, I'll show you now. Now you know how to calculate this E curve, right? Now let us go back to the previous one. How I am getting that. This is the derivation which you need to remember. So we are doing this, right? So you calculated the C curve. From C curve, E curve you are calculating by using this particular, right? So C curve you know how to do. E curve, right? Then we can have one more curve, that is F curve. That's later. So how I am getting this C curve to? I'm changing this E curve to C curve to E curve. That is what I'll show you now. So quantity, known quantity of the tracer, maybe m kgs or moles, is suddenly injected in one shot into the flowing fluid, just like you are introducing through what you call syringe, right? For a very short period of time. If the period of time is long, then your pulse unit becomes pulse. But the unit, if the very short time, your pulse input becomes impulse input. Okay. The tracer concentration in the exit stream is measured as a function of time. That is what you did here. The tracer concentration is measured in terms of time by using this, and you are drawing a C curve, right? In RTD analysis, the effluent concentration versus time is referred to as C curve. This curve is nothing but C curve. This C curve you have to write in terms of E curve. E curve is nothing but excitage distribution curve. So once you get a C curve, the maximum concentration or concentration of the effluent stream increases with the time, reaches a maximum, and then falls, eventually approaching zero. Generally, anything, if it is impulse, you get a bell-shaped curve. If it is a bell-shaped curve, we call it as a Gaussian distribution, right? Binomial distribution, if you know. The Gaussian distribution in the sense, this is the T bar, and it will be a symmetry here and here, like a bell shape. Perfectly bell-shaped is Gaussian curve, right? You know the Gaussian model, right? In mathematics, you might have studied. But generally, if you get a Gaussian thing, then we call it as left side is equal to right side. There is no variance at all. But generally, when you do that, you get a like this curve. If you put this particular thing, the bell may be extending, or sometimes what happens, you get a like this curves also. Some different peaks you get. That means that there is some short circuiting. That is, more amount of the fluid is coming out. Some tail at the one side tells you there is some, what you call, dead ends inside. The concentration of the fluid is not coming out, right? So these are some of the ways by which, looking at the C curve itself, we can tell what is happening inside, right? So generally you get a Gaussian curve. If you get a Gaussian curve, you can, your variance will be zero, right? Because it is perfectly to this side and this side is perfect. So next, the amount of the tracer material, delta M is the amount of the tracer. Delta M tells you how much is the increments. Delta M, the leaving the vessel between T and delta T is obtained by the material balance. Now you know here, there are some, let me erase all this so that I'll come back again. Again, I will come back. Yeah. Now, if you see here, now you see here, there is some fluid which is coming here. There is some fluid which is coming at this time. There is some fluid which is coming at this time. Some fluid 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 like this. It comes differently, right? So if you see, this particular fluid is coming out first. This particular fluid coming out later. This particular fluid coming out a bit later, right? So now listen this, the amount of fluid, the amount of tracer material, that is delta M, leaving the vessel between T and T plus delta T is obtained by material balance. Now what does that mean is, now I want to calculate how much is coming here. Means I know what is this T. Delta T, that is how much is the gap I know. So if I want to know what is coming out between T, and this is nothing but T plus delta T. So this is the material which is coming out between T and delta T. Am I right? This is the material which is coming out from T and T plus 2 delta T, right? So because delta T is constant. So if I want to know how much is coming out from this particular thing, I can do by material balance. That is what I am doing here. Delta M, how much is that? That is nothing but in this, how much is coming? This is delta M1, this is delta M2, this is delta M1. So if I add all that, I get total M. Am I right? So how much I to get delta M is nothing but C into V into delta T. What is C? C is the concentration. V is the volumetric flow rate, because the fluid is going with a volumetric flow rate of V. This V is coming out, the same V, into its concentration, because you are having a detector here. You can measure the concentration into the time of which you are putting. So that it will give you how much of the tracer which is coming out. Am I right? The volumetric flow rate into the concentration into the time. That is what is here. So delta M is the amount of the material that has spent a amount of the time between T and delta T. That is what here. Where is it? Yeah. Yeah. Now I want to measure how much is here. This particular thing is nothing but this material is coming out. This fluid is staying for a distance of T and T plus delta T inside the reactor. Because I am putting outside it, I am measuring it in the sense, I am trying to measure this fellow, this much of the fluid spent T plus delta T inside the reactor. Am I right? You have to visualize something here. Like this here, this amount of the material is staying for T plus 2 delta T inside the reactor. That is what is mentioned here. So equation 1 divided by M, I want the percentage of the material which is coming out. Delta M by M is nothing but delta M is CV delta T divided by M. So I can flip this, C delta T divided by M by V. V we can write M by V, where M is the total amount of the tracer which is injected, right? So delta M by M is the fraction of material that has a residence time between T and T plus delta T. Am I right? So m is delta m is nothing but an increment. M is the total. That is nothing but individual by total. That is what you call as a fraction. How much is the fraction of that? That is the fraction of the material which is spent between T and T plus delta T inside the vessel. So let us define that C into volumetric flow rate by M as E. E, if you put this particular thing as a E or C by M by V, then delta M by M it becomes ET delta T. Because delta T is here, you are putting this entire thing as E curve. Therefore, E delta T it becomes delta M by M. That is what is here. Whenever M is not known directly, M is nothing but the total material of the tracer which you are putting it. It can be obtained by measuring the tracer concentrations in the effluent stream and summing up all the materials. That is what is here. If you don't know what is M, that is what I am telling you. You don't know how much you are sending, then you have how much is here, how much is here, how much is here, and you sum up entire thing. It will give you the total concentration of the tracer. That is what you are doing here. So integral 0 to m dm is nothing but, if you do the integration to this, is nothing but m, right? So integral 0 to infinite Cv into delta t. That is what Cv into delta t. The equation 1 can be rewritten. This equation can be rewritten like this. So 0 to m dm is V is a volumetric flow rate which is constant. You can take outside the integral. Therefore, integral 0 to infinite C delta t. So V you put down m by V, because this integral I took it 0 to m, I substitute m by V is integral 0 to infinite C delta t. So combining this equation and the third equation, this equation, E curve is this and E curve is this, m by V. So you can put E curve as this particular thing. So if I know what is C curve, area under the C curve and C curve, how much is the concentration I know. Concentration by the area under the curve will give you E curve. So integral C delta T is nothing but, integral is nothing but what is it called? This sum or sigma Ci delta Ci is nothing but the area under the curve. That is nothing but m by volumetric flow rate. M is the mass of the material what you are giving by volumetric flow rate. So area under the curve, either a lot of ways you can calculate. That is what is here. That is the same thing I am putting here. Area under the curve. The mean of the pulse. So you are getting a Gaussian, not a some distribution you get. I want to know the mean. Mean is nothing but what is the time spent by the molecule inside the reactor, the mean, right? Different molecules are spending different time. So I want to calculate the mean, like you are getting different marks. So I want to calculate the mean mark. I will add all your marks divided by the students, total number of students. Then I get the mean class average. That's the same thing I am doing here. So mean is nothing but V by V, volumetric flow rate by volumetric flow rate, right? Volume by volumetric flow rate will give you T bar. So this you have to calculate by using. So using this only, this particular formula, we did this. C curve, E curve is C divided by this. So we draw the E curve and based on this, you calculated it, right? So again, I repeat this problem. The data between represents C curve data is given, is asking you to calculate the mean residence time and E curve. So mean residence time is this formula. You have to club. It is just a school statistics, right? It's not that difficult. So area under the curve, there are two ways. Directly you can calculate by using this Ci delta Ci. Otherwise, you can go for Simpson's rule, 1/3 rule or 1/8 rule. Either you can go for 0 to infinite or you can split the interval. That's up to you how you do it. So E curve you calculate, then you draw the E curve. So in the this type of problems is very important. Lot of times he will ask you, he'll give you a C curve and ask you to draw a E curve, and mean residence time he will ask you calculate. We'll do one more problem. Now this is a sample of tracer, some heptane or something was injected as a pulse inside the vessel, is used as a reactor, and the effluent concentration is measured as a function of time. The data collected is here. So T with the C bar, C concentration is giving. The delta Ti is nothing but year 1, but here there is 2. So delta Ti is different than delta T. So you have to put what is the difference between these deltas every time. Construct C curve and E curve and determine the fraction of material leaving the reactor that has spent between 3 and 6 minutes. So he wants how much of the material is staying between 3 and 6 minutes in the vessel and the fraction of materials leaving that has spent between 7.5 and 8.5 minutes in the vessel. So if you calculate this, then we can see if you put an average of 15. So this fraction of material is staying for 15 minutes inside the reactor, and this fraction of materials is staying more than 15 minutes inside the reactor. So in this problem is asking you how much a fraction of the material is between some two time intervals. So you have to draw a E curve and draw the area under the curve and find this area. That area divided by the total area will give you the fraction of material which is staying between these two, right? That is what you try to do. So this is the same thing, E curve, C by C infinite. So C infinite is, you have to calculate the area under the curve. You are going for a Simpson's 1/3 rule. So this is the Simpson's 1/3 rule formula. Either you can do this or directly you can draw a graph. That's up to you. Here he is going for two limits. 0 to infinite is 0 to 10 and 10 to 14 because maximum is 14 is giving you. So he is calculating that 10 to 14, 0 to thing. So he added all that. The total thing is 50. This is the area under the curve. Now we calculate the E curve. E is C divided by 50, area under the curve. What is C? C is nothing but this. 0 divided by 50, 1 divided by 50, 5 divided by 50, 8 divided by 50, 100 divided, 10 divided by 50. So C by area under the curve, individual by total. That is what you did. You calculate that you can see here. C divided by, that is 0 divided by 50, 1 by 50, 5 by 50 is 0.1, 8 by 50 is 0.16, 10 by 50 is 0.2, 8 by 50 is this. So you calculate the E curve, plot the E curve. Now plotting the E curve is this. Plotting this is the C curve, sorry. This is the E curve. Now what is asking you? Is asking you how much of the fluid is staying between 3 and 6 minutes. So this shaded region is what you want. How you do? Either you can do a numerical method because this limit is from 3 to 6. You can calculate the area under the curve by using Simpson's rule or just by calculating. That's up to you. Here he is giving you Simpson's rule. That is what is doing here. So you can see here. So using Simpson 3/8 rule, that is 4-point formula, is calculating x0 to x3, 3/8, fx0, 3 times in between, and then this. This is the formula. If you are having 4 points in between, so h is this formula, and then h you calculate, and then you calculate the area under the curve from 3 to 8, how much you want. Numerical way, you are getting 0.51. So that means that 51% of the material leaving the reactor spends between 3 to 6 minutes. If you see here, so this is the area on the curve. It is 1 almost. Area always it will be 1 because C divided by C infinite is almost 1. So you want this particular thing. If you calculate, this is 0.51. That means that if this entire area is 1, this is 0.51 in the sense 51% of the material what you sent inside is staying between 3 to 6. That is what you are analyzing here. So we need to calculate one more thing is 7.75 to 8.25. Again, you calculate the E curve between that. and then E curve into dt will give you the total amount of the material which is staying. So 0.03. So 3% of the material only is leaving the vessel that has time between this particular thing. So 7.5 or something, or 8.5 in this region. So only 3% of the material is staying between that limit. That is what is giving, right? So either it is up to you how you want to do. You want to use the Simpson's rule, or you want to go for calculating the area under the curve by the number of squares. That's also up to you how you do it, right? So integration you can do by Simpson's rule, numerical methods. So this is one more problem where is will ask you what fraction of material is staying between the limits, right? Yeah. Any doubt till now? Any doubt till now? So you can see one more problem. He is asking you to calculate mean residence time and variance. What is variance? Just now, the variance is this. Integral 0 to infinite t bar square e dt. This is the variance. So you have to calculate t bar. Now for that, t is there, e is there. That is what he is giving you, t and e. T into delta t, you put t into e, because t into e you have to calculate. You put it. T minus t bar, you already calculated t bar. T minus t bar, this minus the thing, you get some negatives, some positives. Then t minus t bar whole square into e. This is what is want. So you calculate. The sum of this is nothing but this integral. Am I right? So you can do that. That is what t bar is integral 0 to infinite t into delta t. So either you can calculate or you can split the limits and use the Simpson's rules and calculate. So this is t into e bar, and t minus t bar e divided by t. So you are getting some 2 peaks you are getting. That means that there is some bypass. Whenever there is a E curve like this, some 2 peaks, that means that there is a strong bypass here. So that is why total amount of the material is coming at a peak of around 2.5. There is one more bypass inside, maybe around at 10, right? So that is what you have to understand from this. And then calculate the variance. Variance is nothing but this. If you can calculate the what do you call integral, it is fine, or you can go for a tabular column, and then the sum of the tabular column is nothing but the area under the this particular thing, right? So you can calculate that variance also. So he is using again the 1/3 rule for the variance again, because since integral is there, you can do by numerical methods also. So Simpson's rule, if you put variance is 2.47. What does that mean now? 2.47 means your mean is somewhere, your mean is around 5.15 minutes. So the material is staying, most of the material plus or minus to this particular thing. How much is that plus or minus? That is nothing but this 2.47, right? That is what you will get from the standard deviation. Other than this standard deviation is the squared of this. Then there is 2 more also. Kurtosis, one more is there. I don't know whether you what do you call come across these terms in what do you call statistics. There is cubed also, and 4 times. Am I right? The cubed gives you skewness. Am I right? Square term will give you the variance. Without square term, it is mean. That is what we call as, what is that we call in, yeah, first moment. Yeah, first moment we call it as t bar, that is mean. Second moment is called as variance. Third moment we call it as skewness, that is which side it is skewed, either left side or right side. Fourth one we call it as fourth square, that is t minus t bar whole power 4. It is called as kurtosis, I think. I didn't remember. I think it is kurtosis. So 4 moments you will get, especially in statistics. So second moment we call it as standard deviation, right? So I stop, I think, here. So next we'll go for later class. So try to do some problems with this, right? Try to do some problems with this. So the C curve is like this. It converts to E curve by using this particular thing, right? So when you are calculating this E curve, if you are getting a like this, that means that you are getting a different peaks instead of like this. If you are getting one peak, it is fine. When you are getting a two peaks, so you have to analyze that there is some what you call bypass or some term which is going, right? So I'll stop here, then go for the transforming into the other one. This is what we call it as impulse input or pulse input. From pulse input, we get C curve. C curve will be converted to E curve. Whereas if you are going for a other one, that is step input, you get F curve. You get F curve. There are three curves: E curve, F curve, and C curve. So from pulse input, we get C curve. From step input, we get F curve, right? That we see in the next class. I don't think I can finish off this F curve now. So C curve to E curve is very important. How to convert C curve to E curve? By using this formula. E curve is nothing but C divided by the sum of the area under the curve. Sum of the area under the concentrations. It will give you E curve. Right. So I stop here. Guru or Yamini, I think now 56 people are there. So minus 1, 55. So 10 people may be absent. Yeah, Guru, you're there?
Yes, sir.
Yeah. So you try to look into this book and then do some problems which are very important. First four problems you do, right? Because you are having some holidays in this what do you call vacation. So first four problems you do, and anyhow I'll ask you for a what do you call this assignment in the fifth unit. So this first four problems also will be there along with some other problems. So try to do now itself and keep it. If I'm not giving any other problems, you can just submit these four papers. That when I put in the website that you call intranet, then you can put it, right? Right now you do it. You take a graph paper and then do it, right? So in this holidays, try to do this first four problems. That is from C curve you draw, calculate the E curve, and then calculate the T bar and variance. That is standard deviation, right? Try to do that four, right? For each and every problem. Okay. Yeah, any doubt? Today I didn't discuss anything, just a recap of the statistics which you might have studied earlier. Yeah. I'll stop here. Then we'll discuss in the next class. I stop the recording now. Yeah, any doubt you can ask me now. Yeah.